Hello. In the last lecture, we learned how we handle a regression model with multiple regressors. The conclusion was straightforward. There is nothing new, nothing different from the regression model with a single regressor. So when you have, and the most general form of regression model is a model with k number of regressors like this. There is a dependent variable y, and it's determined by the intercept beta 0 and a linear function of k regressors. And each of the regressors has their own coefficient. So beta 1 captures the effect of x1 on y when all the other variables are held fixed. So that's the important point. It's a ceteris paribus assumption. All the other variables must be fixed, and then if x1 increases by 1 unit, y is expected to increase by beta 1. That is how we interpret those coefficients. And the error term u has no difference. And to have causal effect, causal interpretation on those coefficients, there are 4 assumptions. The first 3 assumptions are the same thing from the single regressor case. Same assumptions as in the single regressor case. The first one is conditional mean 0, which means that the error term, it has no systematic pattern with respect to the regressors. So when the regressor changes, the error term should show no pattern. There is no pattern in the error term. And second is an IID assumption, which is the most fundamental assumption in statistics. And third regulates the number of outliers. So there should not be the number of outliers should be small enough, which is and the last assumption is a new assumption. And you have a new term, multicollinearity. So multiple regressors have together a linear relationship. So then it's a problem. Multicollinearity is a trouble. So, and this is a new assumption which did not exist in a single regressor case because it is about the relationship among the regressors. So the relationship matters only when you have 2 or more regressors. So in the single regressor case, the multicollinearity was not a problem at all. There is only one, so there is no relationship between regressors, but now we do. So today I'll be talking about the multicollinearity problem. I will talk about examples and symptoms, treatments, and how you interpret some special cases. So this will be the first main topic we are going to study today. Let me go directly. So here is an example. So brief example of multicollinearity here. It's a obviously wrong model where you regress test score. Test score is the outcome, and you regress the test score on student to teacher ratio, but you by mistake included student to teacher ratio twice, or in your data 2 variables were actually the same. They could have different names, but their content could be the same. Then you are using 1 variable twice, so it causes trouble. So in Stata, one of them is automatically dropped. Stata understands the problem and drops one of them. So and theoretically, we can view this the problem of this command as that there are 2 regressors, but the relationship between those 2 regressors is that they are the same. So the relationship between them was the problem. If they were different, then then they two regressors is not a problem. Okay, and let's go to the multicollinearity. So in this this topic, I think multicollinearity is an interesting topic, and it's very confusing, but it is not that difficult to understand, and many students may encounter similar problems in their like essays, dissertations, or later. So I would like to use my own slides. So I didn't like the slides from the textbook, so I'm going to use my own words on my own slides to introduce the multicollinearity problem. So let's think about simple two regressors case. You have an outcome, an intercept, and x1 and x2. x1, x2, and error term. So the problem, we are looking at the relationship between x1 and x2. And remember, the definition of beta 1 is this. Beta 1 is the effect of change in x1. So the definition ended here if you had a single regressor. But because there is another regressor, you have to control for the other one. So beta 1 is the effect of change in x1 holding x2 fixed. So you have to fix x2 and change x1. That's the minimum requirement to estimate beta 1, right? You should be able to hold x2 fixed and change x1. So then, in other words, if you cannot change x1 without changing x2, so whenever you change x1, say x2 should change. x2 cannot be constant. Then you cannot estimate beta 1. It is very straightforward, a very intuitive argument. And this is exactly the multicollinearity problem. Multicollinearity problem arises if x1 has no variation when the other is fixed, or vice versa. So you have to fix one and change the other, but when one is fixed, the other cannot change. Then you have a problem, and that is the multicollinearity. So this is about the relationship between x1 and x2. Let me show you some examples. Here, I will skip this. I'm going to use my own slides. So this is the first example I'm going to consider. So remember, in an earlier example, we considered the percentage of English learners. So in a school district, how many students need English class separately. So that's the percentage of English learners. But now, you can define, alternatively, you may define percentage of English speakers, which is defined as exactly the opposite, the complement of these guys. So that by construction, by definition of those two variables, the percentage of English learners plus the percentage of English speakers must be 100%. So if 20% of students are second language English, 20% use English as a second language, then automatically the other 80% must be English native speakers. So this is exactly this is the multicollinearity. So if you know, suppose that you fix the percentage of English learners at 20%, then the other variable, the percentage of English speakers, is always fixed at 80%. It cannot change, at least in the data, right? So, so if you use those two regressors together like this, then you cannot estimate this effect. There is no ceteris paribus variation in both of them, in either x1 or x2. So this is a simple example of multicollinearity. I will give you a little more complicated relationship. So think about a wage-salary equation. You would like to study how the salary is determined. And the variables you are interested in, the regressors you would like to use are age, A is age, and S is schooling, and W is work experience. All of the three variables are reasonably important, relevant, and good, important variables. So the model itself looks reasonably good. Okay, I understand, that's right. But the problem here is, think about the reality. So most people start elementary school, so most people become the first grader at age 6. And they get a job, they find a job right after graduation, and they accumulate their experience right after graduating from school. So therefore the age is your life consists of 5 years before you enter the school, and the years in school, and the years after graduation, which is your work experience. So there is a perfect linear relationship. Like for example, so if you know, like among these three, if you know 2 of them, the other is automatically fixed. So for example, think about this. Suppose that there is a person who has 16 years of education, so college graduate, and 2 years of work experience, had worked 2 years. Then from the data, he or her or his age must be 23. You know, so it's maybe more than 90% of observations will be 23. So even if this relationship is not perfect, is nearly perfect, still that's a problem. And from these 2 examples, you can see the problem, like mathematically. So intuitively, the problem is the lack of variation, the ceteris paribus variation. So lack of variation when the other variables are fixed. And or in other words, when you fix some variables, another variable can be fixed. Then this guy cannot be separately estimated. And mathematically speaking, the problem can be stated as a regressor is a perfect linear function of the other variables. So a regressor is determined by a linear function of the other variables. Like this, so age is a linear function of schooling and work experience. School and work experience. Or in this example, like percentage of English learners is determined by 100% minus percentage of English speakers. So that's a linear function. So as you can see from these 2 examples, if a regressor is determined completely by some of the other regressors, then you are in trouble. There you cannot estimate the ceteris paribus effect. And then so now okay, I'm going to stop here and we'll continue what's the symptoms, how we can tell if there is a multicollinearity, and what's the remedy to the problem. So see you later. Thank you for watching.